I'm going to start the recording a little early because otherwise I tend to forget it. So better we have a few minutes of pre-meeting. So do you have anything you want me to load up? And I can make you also the shower now of slides. So let's see, close that and share screen.
Yeah, so yeah, I will be sharing screen and yeah, so my slide should be fine. Let me just to try it just to make sure that everything runs smooth.
Okay, and I've already made you multiple people can share slides, and if you want to do it later, Jim, you can do it too later on.
Can you see my screen?
Yes, I can.
Okay. Okay, then it should be fine.
That looks good. That looks good. Okay, so we are ready to roll. I want to thank you very much, and I'll do that when people are here too for coming this morning.
Oh, it's my pleasure. I'm looking forward. I would like to hear ideas, questions. It's kind of very stimulating. Yeah.
Well, see, this is now. Have you ever spoken to a science fiction group before? Or
No.
This is where the humanities meet science, and probably a different audience than you've had for most of your talks.
Right.
And that will mean they will be thinking of plot and possible societal issues rather than technical and scientific.
Yeah, yeah.
That was my husband who just came here. He goes on his own computer, so you see him floating by occasionally. My son's coming too. But there's a number of people that said they were coming. I just hope they all remember to actually do it. And oh, it says we had 2 people. I got to keep watching waiting room. Yes, there we go. There's 1. There's 2. I get talking and forget to watch the waiting room. So we have a channel now on YouTube. Is it all right if we share on YouTube once we start loading? We haven't gotten any of our videos up there yet, but we're working on it.
Yeah, it should be fine. Yeah.
It should be fine. Okay. I should get everyone's permission. So far, nobody was upset about that or had any problem. And Nancy is here. Hello, Nancy.
Hello.
How are you this morning?
Fine.
I just saw Nancy yesterday. Yeah, we're bumping into each other like atoms in Brownian motion. So Nancy, is your New York person going to come, do you think? The one that you
I don't
invited?
know. He had a meeting to get to at 9 New York time, so whether he'd be home or not, time I
Well, we'll just wait. We're still a few minutes early, so we'll see. Sometimes they come in later as well. I was sending out reminders. Maybe I should do a little more. Let's see. Oh, we got one more who thanked me for the reminder. He would have forgotten it. Let's see about this second person. Oh yeah, 2 more. Let me see who else I can invite that usually comes unless they forget. Boy. Oh, I know. She comes a lot, so I better remind her. Oops, I have to forward, not send a new message. Let's see. I've been sending out all kinds of notices, but you never know. Let's see. Reply. No, I don't want to reply. That's what I want to do. Forward to LipTac. There we go. So that may get several more, and got to go back and check my thing. See, is anybody else showing up yet?
I'll be right back. I have to get more coffee.
Oh, sure, sure. Now they're still
Okay.
checking in with me. and trying to think who else might show. I think the one that's doing the recording said he couldn't be here. I sent him a reminder, but I think he did say he couldn't be here this morning. My son Chris has not checked in yet, so send him a reminder. I think I did. Oh, there he is, so I don't have to do that. There's my son Chris. Okay. Now we have a couple stray astronomers who say they're coming. Let's see, who else? Who else?
Be right back.
So absent-minded because they're like me, getting older. It just doesn't hurt to remind them at the last minute. Let's see. Okay, here's another one. Oh, I know one. He said he was coming too.
Good morning.
Good morning.
Morning.
How are you? Look, everybody's there.
Well, they're filtering in a few at a time. As I send out reminders, they're going, oh yeah.
And
had
good
forgotten.
morning, Professor Gang. Welcome to.
Morning.
Let me see. We're getting more people now,
Yeah,
and I know.
and it is still not even 9 o'clock. So
Oh, good.
you're seeing the early birds.
That's true. Now I have to go through. Oh, here's one that might come, but no, maybe not. Let's see who else might come. I'm just going to go through some of my list here. Let's see who. Oh, he said he was coming. That little Dickens. Okay, send him one. Let's see.
Maybe that's me. So you are recording today, right?
Yes, yes. You can hear me. Can you hear me?
Yeah,
Oh,
perfectly.
okay. Yeah.
That's
Yes. I remember to do it to cloud. We're all set.
Our esteemed colleague Brad Story, the Associate Dean of Science in at the University of Arizona, he loves these presentations, but he can't be here in person. So he's excited to get the recordings.
Oh, yes. Well, we're still working on getting those up, and I just couldn't even do all the steps it wanted me to do to share with the guy who's actually the media man. So I'm asking him to start his own account, a Google, his own YouTube account, and share with Google so that we can get this thing going, because I couldn't get through it. It was just confusing me, and it didn't like things I was doing. So it was all very security conscious. Hi, Phil. We have a new person. Phil, are you in the local area or are you elsewhere?
No, I'm a friend of Nancy's.
Oh, this is
I
the
live in
friend
New
of
York City.
Nancy.
She mentioned this was going to happen
Well,
today.
welcome to our group, and we're still expecting a couple more people. But as they come in, oh, Tim Sapa wants to be admitted. There he is.
What's it like in New York City?
It's a beautiful day today. It's a bit chilly, but it's clear blue skies. It's very nice.
Oh, lovely. Yeah, autumn in New York can be fantastic. Which borough?
Queens.
Oh, up north.
It's kind of chilly here in Tucson too. I mean, last
For
night it
Tucson.
got down into the 60s.
Yeah, that's pretty cold for Tucson. I used to live in Tucson, so I know.
Okay, I got a note from my husband. He doesn't speak to me. He sends me notes. He said, your audio is slowing down, so shut your other browsers. I want to shut this one by accident. He has a sign he hangs on the door there. I'm not supposed to come in when he's having meetings, so.
You have the most tactful husband ever, Gloria.
Yeah, maybe. All right, so we're actually, I don't know what other people have because mine says 9:03. Are we after 9 or at 9?
9:02.
We're a little after.
A little after. Well, I want to introduce, oh, here comes Karen. See, if I had reminded people, it would not come. I want to tell everyone how lucky we are to have Professor Gang coming to speak, because this is the stuff of which dreams are made of. And it is the material that has for so long thrilled science fiction writers, miniaturized robots and nano beings. So I won't take too long. We have his slides, I think, all set up. And what else should I say? He's, well, oh yes, live transcription. Let's see. Oh, where is it? Oh, here it is, live transcript.
Request.
Table. There we go. There, we have a person who requires live transcript, and I had spaced that out. Okay, so our guest is very welcome here, and he is featured in a number of national publications for his cutting edge research on self-replicating nano robots. And there are numerous applications that should be of great interest. I think we have one more person. Oh, yes. Okay, that should be of great interest to people in our fields. And I will not belabor it. He is from Columbia University, and they're, I believe, electrical or engineer, some kind of engineering. I forget the exact department, but he can correct me, and I welcome that. So I'm now going to turn this over to Professor Oleg Gang, and just let me know if you have any problems with share screen. Thank you.
Good morning thank you, Gloria. Good morning to everybody. I'm excited to share with you what we're doing. Usually I don't present at this type of forum. Even so, when I was a child, I was reading quite a lot of science fiction. I think that's really why I became a scientist, trying to find the way to realize those ideas. But now I think as a scientist, we also need a kind of another way to communicate, not only to tell where we are now, but also somehow to get inspired by people who are thinking about science, science fiction. And because in many cases, those ideas are really driving research and pushing the boundaries of what is possible. So my task today is really just to tell you not what is possible to do, but what not is possible to do in 100 years from now, but what is possible to do today. And so why it's exciting and why it can change our lives. So as you will see from what I will tell you, it's not like one application or we can make better, I don't know, sensor or better electronic device. It's rather kind of conceptually different way to think about how we can create materials and what really material mean, or what the system can present. To what degree we can push materials toward, being kind of not necessarily artificial living materials, but somehow to have some features which typically not found in a conventional. So this is essentially my goal. And I understand that you not necessarily have scientific background, so I will be trying to simplify it and to have pictures. I still understand that maybe not everything will be clear, so feel free to ask me. I'm not sure that I will be able to see the chat when I'm running the presentation, so just feel free to interrupt me and I will be happy to go and so on. But of course, we can discuss it also much more after. So
that's a good idea, because chat can sometimes interfere with people's reception. It actually caused the whole thing to crash on me. So I have to remember to stay out of chat while you're presenting.
So let me basically start the presentation. So I am both at Columbia University and at Brookhaven National Laboratory. At Columbia, I am at Department of Chemical Engineering and also in the Department of Applied Physics and Applied Mathematics. And at Brookhaven National Laboratory, I'm at Center for Functional Nanomaterials. And so those two institutions located not very far from each other, kind of geographically like 60 miles, but it's not very close. Particularly in New York, 60 miles can mean you never know how much time it's exactly. So, but in any case, so when people ask me where I am, I'm saying, okay, I'm like electrons split between two locations. So, but in reality, I'm spending probably kind of half of my time in one place and half of another. And so most of the, we have different PhD students and so on, which kind of in university, but very often we're coming to Brookhaven National Laboratory to do some more advanced characterization, and I will show you some examples. And it does require really state-of-the-art instrumentation, which is maybe just one of the kind in the world or in United States. So the whole notion of nanotechnology, it's not something new, even so it becomes now very publicly kind of known. But this idea that was first, and you probably know this very well, was kind of discussed by Richard Feynman in 50s in his talk, There is Plenty of Room at the Bottom. The idea was that what if we can organize atoms kind of deliberately in a particular type of organization we would like, we could potentially enable different types of properties which doesn't occur kind of naturally. And so that's kind of was a long way from the idea of really have this ability to various realization, which became kind of more evident in the last couple of decades. So first of all, what is nano, right? So again, I'm not assuming anything. I'm just kind of like, maybe all of you know, but I will just take this kind of assumptions that not necessarily. So what I would like to stress, there is a whole reality which we can see either by naked eyes, or we can see with a relatively low-tech optical microscopy. And this is kind of somewhere lives in this area, 1 micron or few microns and up, which is, then there is a whole, universe of very small particles, which is high energy physics and so on, has been dealing also for a long time, which is smaller than atoms. And then there is this universe between, let's say, 1 nanometer to 1 micron. This is where variety of objects can exist in the form of virus, in the form of biomolecules, in the form of nanoparticle, which I will tell you more, which essentially they complex enough, they compose of many, many atoms, but at the same time, it's very difficult to create them because we don't have really good means to operate on this scale. And so that's really the challenge, that those systems are very complex. It's, unlike, let's say, chemistry, they don't contain 5 or 10 or 20 atoms. They might contain millions or billions of atoms. And so going back to this question, how we can arrange by one to make different structures becomes kind of very challenging. So, I like a couple of slides which I show you just because it's very graphically shows how quickly we're going down to the scale. This is the scale of our regular life. We kind of can scale down to mouse. This is a mouse, this is ant. And then we scale down. This is pretty much the limit which we can see by our eyes. This is a hair. It's approximately 100 nanometer in diameter. This is a particle of pollen. This is some kind of tick. And so below that, we're reaching essentially red cells. And below this, we're reaching viruses. And this is already impossible to visualize. By conventional means, we need to have electron microscopy and so on. That becomes already quite high tech. As well as soon as we're going down, we're reaching kind of where biology operates in terms of molecular biology, different biomachines, different proteins, and so on. This is kind of the type scale. And so from engineering point of view, we would like to say, okay, those are kind of components which nature created, but what if we can make components on this scale? And again, this is a scale from few nanometers to tens of nanometers. And so this is kind of what is become challenging, how we create individual components on this scale, right? So this is where we're going to already, this is on, let's say, atom and molecular scale. And the dream was always, if we can create those objects on the scales of, nanometers, 10 nanometers, and so on, and not just create different type of geometries and different type of architectures, but also somehow to make them functional. And what I mean by functional, it means that they can be potentially reconfigurable, they can potentially transduce energy from one form to another, they can potentially do chemical reactions and do many different things. But again, the whole point is designability. It's kind of very, very important parameters. And so we need to have means to realize something of this kind. And that has been the driving force, including variety of science fiction, obviously, suggestions how those robots.
Somebody is having interference. Could everybody mute your microphones, please? Please mute. I'm going to mute mine.
So, the question, what I really want to stress, it's a question that we can draw a variety of pictures and say, okay, it would be great that it can work. The problem, however, that we don't have really means to create something like this. Again, I just wanted to stress that chemistry operates well on a scale where we need to create, structures which doesn't necessarily contain a very large number of atoms or not high degree of complexity. From other point of view, we know that nature is able to create a variety of different things, which might be on a scale of nanometer, but it also can be scales on millimeters or even larger. And so the nature does it somehow very specifically, creating those structures and so on. And so from this point of view, it becomes a question, first of all, the question how we can create different type of nanoscale objects. And the second point is how we can build from different components more complex systems. So before I go and discuss how it's done and what we can do, I wanted to stress also another aspect. What is special about nanoscale, even when we don't talk about any complex biological molecules and so on, but are we going to talk only about, conventional elements? And so the interesting part that we all know the properties of materials on the macro scale. We also understand and know in many cases the properties of materials at atomic scale. However, it turns out that we're taking the same type of elements from the periodic table and we repackaging them, and by repackaging meaning we making some kind of nanoscale object of from them, we have access to the new material properties. So I'm showing you the example here because it's nothing stronger can be than those are very simple example. We all know how gold look like. It's look yellow when it's in its macro scale form. But as soon as we make nanoparticles from gold, you can see it has absolutely different type of color, and the color actually even changing with the size of the particle. This is example of so-called quantum dots. Maybe you didn't hear about them, but right now many high-end TVs already now sold with those kind of quantum dots. Those are nanoparticles which can emit light. And you can see here essentially all these different colors require only very small variation in particle, in changing particle diameter. So what I wanted to stress, there are a variety of effects associated with the confinement of atoms in a particular this kind of repackaged structure, and those confinement lead to different quantum effects. There is a very large surface area which also play a role, and all this allows us really to access new properties of material. And this is super exciting because we don't need to invent or we don't need to find. We cannot invent, but we cannot really need to find any additional element which doesn't really, maybe potentially doesn't exist, but we can just reuse those elements and discover new properties if we're able to package this. So it was tremendous efforts going on in the last maybe 2 decades and so on in our ability to synthesize different nanoscale blocks. They can have different shapes, they can be composed from different materials and so on, and that's really led to the discovery of many types of nanoparticles. I'm not going to talk about how it's done and so on. That's a separate topic, but I just wanted to let you know that this is a new form of material which carry new properties, and it's exciting to think about this as our elemental block building now, let's say, different types of systems, not from atoms, but from those types of particles. This has become really the question, how by having all those different building blocks, how we can build more complex structures, how we can enable a new material properties. So this is just example, that what I was just telling, that they can be in a well-defined shapes, we can vary their composition, they can vary their sizes and so on, and that give access to the whole kind of universe of different materials which were not available previously. This, again, in terms of applications, I just want to give you some kind of ideas. I showed you some optical applications where, material can change, for example, the way how they can emit. It's possible to consider all those materials might have also, variety of those materials have chemical activities, and they're used in catalysis and other applications. Some of those materials are used for drug delivery or for specific other applications in sensing or biomedical applications. There is a kind of all range of different applications which is available for, potentially available for them. What is also important is, which is when we kind of coming from the point of view of individual particles, but asking, okay, what if I can organize them in a complex, fully kind of architecture and prescribed structures? What properties they can enable? So I'm just giving you this kind of one example of what is shown here up front, because this is probably the most, impacting from the point of view visually. We all know that typical, if you put this kind of straw in a glass, that's how it's going to look like because of the refraction of light. However, it has been discussed theoretically that in principle, if I can build materials in a way how I prescribe it from nanoparticles, I can create very, very different, unusual properties for example, for light manipulation. We can create materials which can essentially demonstrate some kind of this effect. And you can say, okay, is it just curiosity? It's not, because all these questions about how we can bend light, how we can make stuff invisible do require essentially, it's not, we don't need, we still can obey the laws of physics, but we need to create materials which will be able to do it. So it's interesting, this is an example where theoretically those questions have been discussed and people even have particular design, again, computationally, but this becomes a problem that we cannot realize it. We don't have means, we means as a humans, we don't have means to organize because those materials in particular structures, because it does require essentially to build, some type of architectures from different types of nanoparticles, which will be organized in some particular way. So, obviously, you can say, okay, so what about all our electronic industry? And this is exactly why I wanted to stress here. It was huge advances were made in several decades, for example, in the electronic industry. And this is, I'm just showing just as example, the evolution of, electronic industry kind of in this example, what a supercomputer could do in 1985 and what Apple Watch can do 30 years later. And essentially they operate in a, Apple Watch is actually outperform as supercomputers. And you can compare, tremendous difference in the amount of energy which was consumed then and consumed now, not talking about the price. So, and size, right? So all this tells you that, yeah, definitely we have seen such a progress. So what is the challenge? So why we need to consider something else? So, and this comes to the point of how in general we fabricate materials, right? So again, as humans, we fabricate materials kind of typically, I would call in a serial way, right? So we have materials and we have, different processes where we kind of either adding something or taking something from the materials. And this is, shown in those examples. And while conceptually, it's not what we do on a very small scales, it's not conceptually different from what we do on a very large scales. We have better means using, for example, lithography, ion milling, and so on to control small scales, but it's not, again, conceptually very different. So I can just wanted to illustrate this in this picture on the top. This is a Ford conveyor line for assembly cars, more than 100 years ago. And this is Intel fab also quite recently. And so again, what I wanted to stress here, we're dealing with a much higher throughput. We can now assemble billions of transistors, but conceptually it goes one by one. If you look at the way how nature does it, it does in a very different, rather than serial, it does in a parallel approach. This is example of something which we'll call liquid crystals, and liquid crystals kind of very well-known materials have been around for a long time, have been used initially in electronic watches, have been used in TVs. And so I'm sure that all of you have heard about them. And so this is a very simple object, but even such simple objects can self-assemble, meaning that they can organize in some type of structure simply based on the way how they cooperatively interact with each other. Obviously, in biology, we find much greater complexity of organization of cells with different components and so on. But I wanted to stress all those processes here, they're not really, we're not getting this type of structure by adding one by one, neither any biological organism. Somehow there is certain self-organization which arise together and lead to the formation of quite complex structures. So there are many, many examples, and you will be surprised to see that a lot of phenomena which we see every day, from washing hands with a soap, because essentially soap has this kind of two parts. One part of the molecule likes water, another part of the molecule doesn't like, and that leads, for example, to the organization of something which we'll call micelles, and they can contain small pieces of dirt, and this is how soap works, right? I mentioned already liquid crystals. There are a variety of other systems, both biological and not biological, which can different complexity of interactions between different components can lead to quite complex structure. So what I wanted to stress now is asking this question is, let me just summarize what I was telling you. From one point of view, we have access now to the new materials in the form of, for example, of nanoparticles, which allows us to access new properties. From other point of view, we're using traditional ways how we assemble materials kind of one by one, even so we're talking about very advanced ways of fabrication like nanolithography used in electronic industry. At the same time, I'm stressing there is another way to assemble system, not kind of one by one, but this through self-assembly. And so, however, the problem is from engineering point of view, we don't necessarily always have control. Most of the time, we don't have control. Yeah, something can assemble, like, those micelles from soap in some type of structure, but we cannot deliberately, direct what type of structure it will form. And so from engineering point of view, it's a huge limitation. Many things happening, but they're not under our control. So the question becomes how we can provide some kind of guidance to those systems that they will deliberately form kind of prescribed structures, or maybe even not just the structures, but prescribed systems which can operate and do many different things, right? And that becomes a question, how to do this. Why it's again become important, if we can provide those instructions on a very small scale to those building blocks, we somehow address all these kind of problems which typically exist in current manufacturing. And what are the problems? The problems, I'm using this computer numerical control machining, which is quite old, as just another example of serial approach. The problem is, conventional approaches doesn't allow us to build three-dimensional systems at nanoscale. They don't allow us to integrate, for example, inorganic, anorganic, and bio-derived components together. Much was done in the last decade in additive manufacturing using 3D printing, right? Obviously, everybody knows about this, which does address the problem that we can build in three dimensions, but at the same time, we cannot really go to very small scale. So coming back to this point is we have nanoparticles, which is newly engineered objects. We have natural and de novo types of proteins, and all those kind of components can be either taken from cells, or it can be synthesized. And it would be great to think that we can now establish some ways to organize them in a way how we would like system to be. So really, this is type of problems that we're trying to address. So how are we doing this? How are we approaching this type of problems? So what I will tell you about is how we approach this using DNA. So DNA is obviously everybody knows today, it's a material which carry a code of life, right? It's prescribed production of different proteins in our body and orchestrate to some degree, different components, how organism is developed. So we wanted to use DNA not for its biological function, but we want to use it as a kind of smart, and by smart I mean that materials which we can program, which can be barcode to some degree as a barcode for interactions between nanoparticles. So why we're using DNA for that reason? We're using DNA, first of all, for the reason that it has very particular sequence. That means if I'm attaching this type of sequence, for example, to the nanoparticles, one nanoparticle can interact with another nanoparticle in a highly, highly specific way. So just to remind, the way how two DNA strands can connect to each other, we need to have DNA has a certain kind of sequence of those 4 letters, and particular combination of those letters. If they're matching on 2 strands of the DNA, we call them complementary, and they can connect and form the duplex. If there are some mismatches between those letters, the connection might be bad, or they might not form at all. And so this is essentially allows us to use DNA as a kind of addressable building block. That's kind of one application of DNA which we want to use. So imagine we have different nanoscale components, which shown here as a Lego block. And this kind of barcode, which I'm showing here, that's something which DNA can provide us. Through those letters, we essentially can graph DNA to nanoparticles. And so if 2 particles will have complementary DNA, they can connect. If they don't, they will not connect. So that's kind of way how we can digitize and prescribe how particles can be connected in a highly specific way. So, and one can imagine if maybe we can even develop the strategy, how having multiple building blocks, encoding how each of them will be interacting with another one, they will be able to connect in a particular way and to form particular structure. It sounds like a dream, but if you think back, kind of the whole point of self-assembly is that we really need to provide instruction to every block how they need to interact with each other. In reality, of course, it's a little bit more complex than that. We not only each block have to interact with each other, but there is certain kind of cooperativity, how they interact together, and that can lead to the structure. And so the question we're asking, how we can create kind of design materials, what level of instructions we can provide, how to do it, how realize it. And you can see this like many, many questions. So I will show you that this is not a dream, that we can realize those ideas in reality, and we can build variety of systems using DNA as kind of programmable materials, which allows us really to build those types of organizations in a rational way. So as I told you, we can take nanoparticles, we can attach DNA. This is a short DNA. This is not DNA derived from any biological organisms, completely synthetic, relatively short, maybe 20, 50, 100 bases strands. We usually getting them by ordering them from manufacturers. So we glue them, and by gluing that we have some chemical reactions which allows us to graft them to the particle surface. In this example where we have 2 types of particle which have complementary types of DNA, blue and red are complementary, and when we design this particular shell, it's not 1 DNA per particle. 10 nanometer particle might contain 50 those DNAs, and so particles interacting through these DNA shells, and they can form, for example, well-defined ordered structures. We call it lattice. And so depending on all the specific details, it can be particles of different shapes, particles of different materials, we essentially can form different type of organization from those materials. And again, the significant part of what we have been doing in researching is trying to understand. I told you before that they're so small you cannot use conventional, optical, for example, methods. Even electron microscopy, which is very, very important tool, it's difficult to use because those structures are three-dimensional and electron beam cannot go through because it will be absorbed by all these metallic particles. So we have been working in using we have been using advanced characterization facilities, which I will tell you in a moment, that at Brookhaven National Laboratory, which allows us to visualize not just, overall material, but kind of see on a particle level. So what you see here, this is something which we call nanotomography. So probably most of you are familiar with the CT scan, which is kind of done for medical purposes. And you can imagine now if we have beam, which is maybe only 10 or 15 nanometer in size, we can use this type of beam essentially to do CT scan for our samples, and we can visualize essentially each particles in 3D. What you see here, it's not a simulation. This is data which was obtained, and so with each yellow particle, it's essentially information which we obtained from the experiment, and we're able kind of reconstruct it in 3 dimensions. So this is again, this is just to give you kind of a reality sense. This is a very complex experiment that does require state-of-the-art facilities and high expertise from different people who are involved in helping us to figure out this type of structure. This is where this experiment has been done. This is National Synchrotron Light Source at Brookhaven National Laboratory. You can see it's a, it's a larger than football field facility. It's probably one of the best in the world right now, and that's again, that's something which is allows us to use highly focused X-ray beams for visualizing this type of structure. Just to give you the sense of reality that it's the result of work which is gone through, which is done through kind of really enable us with information about those structures. So I wanted to tell you what I told you so far is that how we can use DNA as an addressable glue, for example, to bring particles together in a highly specific way. I also would like to tell you now that DNA can be used as a structural materials. So when we think about DNA, we conventionally think about duplex, and this is its typical representation, but it's possible to create much more complex structures from DNA. This is what you see here is conventional origami, right? So if one take 2-dimensional piece of paper, you can fold it multiple times, right, to create, for example, different shapes. It doesn't have to be piece of paper. You can take a wire, and this is wireframe origami, and you can build different types of shapes from this. So approximately 15 years ago, it was proposed that it's possible to fold DNA in a kind of analogously to this wireframe origami. And so the idea is essentially shown here. We can take a very long piece of DNA, and this long piece of DNA can be folded by providing different types of staples, which can connect DNA at the different places together, and that will result in a folding. So it's again, you can think about this in the following way. While for conventional wireframe origami, we use our hands to deliberately in some particular place to fold it in, create shapes. Here we can have those programmable staples which can bring together different parts of DNA through this kind of complementary interactions. So it's possible to realize, people initially realize it in 2 dimensions. Later, people realized also that you can really build 3-dimensional shape. This is an example from our own work where we can design to build this octahedra, and that's something which we can visualize using electron microscopy in 3D. So we know that it's not just a model, but we can really create this type of object. So why this object is important? Because now we create a completely engineered structure from DNA, and we can integrate the structure with different nanoscale functional elements. For example, we can connect with gold particles, which I already mentioned before, or light-emitting quantum dots, or even with proteins or enzymes. So what it gives us opportunity really to create this kind of nanoscale brick, which has very well-defined structure as defined by the, this DNA frame, but it also carry material inside which has certain kind of functions. So we call this kind of models, we call material voxels, because essentially we can build in space using this as our elemental block. So you're probably familiar with this picture of Escher stars, just kind of remind me. So in this approach, we essentially can connect different building blocks through vertices to each other, and that's result in the formation of larger scale structures in 3D. I'm obviously not gonna go into the detail, but I think conceptually it should be clear. We can encode using DNA what type of object will go inside of the frame, because we have DNA here on the particle surface. We have DNA inside which will complementary. For that reason, we know that, for example, a red particle gonna go in octahedra DNA. We have DNA at the vertices, which essentially prescribed how one vertex will connect with another. They don't have to be the same. Here we have one type of DNA, here we have another. So they have kind of different barcodes, and they know to which ports they need to connect. And so we have been developing different ways how, using this type of idea, we can build really three-dimensional complex materials by organizing all these different type of components. So,
Dr. Gus, let me interrupt for a moment. It's not a question, but I'm a math teacher,
yeah.
And these pictures, these diagrams are so exciting. They go back thousands of years with the mathematics, but here it is. It's right in the center of the technology of the 21st century, and this is the kind of thing that just gets youngsters and college students excited about taking their math classes.
Yeah, you're absolutely right. Yeah, I agree with you. And I can tell you even more than that, we not necessarily always know with something which we're working with the computational people, what will be proper algorithm to design it. So we know we can already realize them in laboratory kind of more intuitively, but I think that bringing the math and all this kind of power of computation really to have predictability, that's something which still need to be done.
Oh yeah, cool. Well, thank you. We'll get our kids working on it.
Yeah, thank you. Yeah, so what I wanted to stress also that we not necessarily can form only, what I told you, like different periodic structure, like lattices, which I showed, but one can imagine how you can program even the shape, which might be kind of arbitrary shapes. This is kind of, what if we want to build some robot from those building blocks? So this is just, again, simple example shown here that we can integrate particle with this DNA type of frame. So what I wanted to stress here, we can create kind of alphabet from particles. So those different types of particles essentially represent different ways how they can connect to each other. This is like T connectors, this is like L connectors, like I, Y. So it kind of depends how many connectors will be active, and they addressable. They have, red connect to red, blue connect to blue, and so on. So, and in this case, we obviously can design different types of simple organization, but turns out that we can, by combining different types of connectors, you can simplify the design. This is like a low resolution version here, and all these different 5 types of particles which we use here have been simply mixed. And if you design it properly and you kind of account for a variety of effects, you can form this type of structure, right? This is, again, I wanted to stress, this is obviously very, very simple structure, right? It's not the point. The point is this structure is self-organized, and you don't need to do anything except just taking those particles here and simply mixing them and depositing on a surface. So sometimes people ask, okay, so I can see that you can form something like this, but look at other guys, right? Some of them are misfolded, some of them missing leg, some of them missing arm, and so on. And I guess this is the same type of answer, which is essentially will be in nature. You have different mutations. It's not everything forming perfectly. In this particular case, the yield of assembly of purpose structure, it's approximately 5–6%. But it's a small yield for now, right? First of all, in nature, as we know, the yield of creating organism is significantly lower, right? But another point is just kind of baby steps right now towards this direction. So The other point, sometimes it's kind of important to stress, and I wanted to say, okay, if I told you from the beginning that we want to create materials which might be exhibit different types of properties, and so somebody can ask, but all this is connected through DNA. DNA by itself, relatively gentle material. You need water environment, you need particular, relatively narrow temperature regime where you can operate. But what if I want to create materials which highly desirable, maybe optical properties. I wanted to take it to space. It's not going to survive, and it will be absolutely correct. For that reason, we have been also working on how we can convert essentially those materials from its fully kind of as created as form with DNA in nanoparticles into the materials which will be, for example, fully inorganic. So we develop, I'm showing you just one example, we develop this approach where we create kind of a replica. So this is where green struts represent DNA, we form this kind of complex organization, and we develop this process where we form silica, and silica is kind of the most abundant probably material on Earth. It's silicon oxide, right? So it's essentially the sand, which replicate exactly the same shape as before. Essentially, DNA got coated, and then through the process, it becomes so solid that we can go to the very high temperature, high pressures, high radiation conditions, and we can essentially verify that it becomes resilient. This is just example of the structure. Again, I want to stress it remains the same in the same architecture. All those pores are open how it was before, and this is kind of example of of the silica material, and these black dots. Those are nanoparticles which we from the beginning place in the structure. Well, I'm not going to discuss about different properties. I just wanted to tell you that there are different ways how we're investigating how we can transfer from having DNA from the beginning. Then we can template DNA into different types of materials and using different kind of processes, and this can be superconductive, magnetic, semiconductive, different composites, and there are a variety of properties which now we can enable, and we investigating these new properties because we now have access to a different type of architecture and different types of materials in a new form. The other aspect that I wanted to stress, it's a question that we can not only organize inorganic materials like nanoparticles, which I showed you, but we also can organize proteins. Probably everybody today knows about protein crystallography, which is very, very important for revealing the structure of proteins. But protein crystallography essentially doesn't allow to maintain the function. So, but what if I want to combine and build kind of synthetic system which will incorporate different types of proteins, but we still need water and we need to have certain organizations. This is just an example of something which we recently did. We took ferritin. Ferritin is important protein in our body. It can carry iron. And essentially we're using DNA here to organize them in some arrays, and we can release iron, and ferritin becomes now in this other form. Upper ferritin is the same protein, but now without iron. And while this release of iron can be done in a way that the whole structure which we assembled from ferritin, it's still maintained. Again, this is just to realize that this is something which we can visualize and so on, which is very, very significant, but not only showing picture, but kind of verify quantitatively that we can form this and how the process goes. I'm not showing this, but just show you simple examples that this is what we extracting from electron microscopy. Can we even visualize this type of structures in 3D using electron microscopy types of methods. And so, again, this is just stressing that all our advances in ability to create materials, they tightly connected with our advances really to quantify them and so on. So I would like to finish my talk by just saying, I showed you various examples where we moving toward creating structures which is fully prescribed in 3D, kind of with a variety of architectures down the road, incorporating particles, incorporating also proteins and so on. And so the point that I wanted to stress, which is super exciting, is that now we can imagine that we're not only building materials which are static, we can create potentially materials which can be dynamic. I call them animated nanoscale system. I don't want to call them anything like artificial life, or anything of this kind, because they're not living, but they can perform variety of, potentially they can perform variety of function. So what we envision that, this is, our material system, which can be reconfigured in different states. Imagine that, it can receive different types of signal. It can be molecular signal, or it can be even physical signal like light pulse or something like this. What if we have also certain kind of circuits for processing those types of signals and making decisions, and those decisions now provide command to our materials how it need to be reconfigured, how one particle go to different place and so on. It might sound far from where commonly kind of accepted, but I can tell you that we have already various experimental realizations in initial stages which show that it potentially possible. It is extremely exciting because it's essentially allows create those materials which can respond to different stimuli, but in a highly specific way. If I have molecule A or molecule B, the system will make potentially different decisions what it has to do. We envision that, because those systems can reconfigure into different states, and they built, let's say, from nanoparticle, which performs certain functions, so material can change those functions. For example, it can rotate light in one way, as shown here, or rotate light in another way, if it's going to be reconfigured from one chirality to another type of chirality. We obviously, it's maybe too early to say, but it's not but for realization, but we also thinking that potentially those materials can adapt to different environment and maybe even evolve. And so it's, again, that's need to be addressed, but I hope that's something which can excite you to think about really material system which can evolve, and we essentially can, the same way how we can, have fruits and vegetables maybe deliberately modified to get different tastes and so on. We can not necessarily have to search for materials. We can direct the evolution to get materials with particular properties. And obviously, because all this relies on certain interface through molecules, through DNA, but down the road to the materials, we can think about different ways how those types of material systems, and again, I'm stressing this is not just a material, this is a material system which contain many different components, has ongoing processes, how they can be directly interfaced or maybe even communicate with biological system, because at the end of the day, they might using the same kind of level, the same common language of communication in the form of proteins or DNAs and so on. So kind of just to summarize, what I told you today is about how we can use DNA as a programmable material to create different types of nanoscale simple building blocks, like, for example, those frames shown here, that we can integrate them we can with different functional components like proteins or inorganic particles, and how we can deliberately connect them in a more complex organization, again, using DNA encoding between those material voxels. And down the road, those systems can be also dynamic and reconfigurable and so on. So that's pretty much what I wanted to share with you. It's exciting research, and I will be really delighted to hear your questions and suggestions. And yeah, and feel free to reach me out if you would like to discuss anything.
I'd like to start. May I start?
Sit down.
Okay, I'm having to come to my husband's computer because I had the usual problem. I'm going to work on solving that. Mine froze. So, and he's taller than I am, so you're going to see about this much of me. Just, oh, he said tilt the screen. Oh, there I am. Yeah, okay. So, I think have we ended the share screen? Then that's good. Maybe my computer recovered. It was having a problem. It was freezing. So go ahead, Bruce.
Yeah. So a lot of us are going to be including this in our science fiction, going forwards. I'd like to ask you, way back when you were a child and getting interested in science, what was your favorite science fiction?
I think probably you know this. I grew up in Soviet Union, so in Ukraine. Now it's Ukraine, but when I grew up in Soviet Union, one of the I don't know if you're familiar. There are writers in Russia, Strugatsky. I don't know if you know. No. There is another is Stanislav Lem.
Oh, very famous. Yeah.
And I think the one particular was what probably the most exciting for me is I forgot the name of this novel. It's about the ocean, which the whole planet, it's the ocean which recreate whatever people's in thoughts in reality. I don't remember. It was what's the name of the book?
Solaris.
Yes, exactly.
Oh,
yeah, Solaris.
oh.
That's probably kind of like somehow what I always like about science fiction, when there is not only the scientific component, but there is also psychological component brought it together. I always felt the whole point of science fiction is bring people into the unusual circumstances and somehow to show different types of people. So for me, it was always not just a science fiction, but also the connection between the science fiction and the human kind of in the picture. So that was probably, and maybe for that reason, Solaris is one of those.
Oh, okay. Let me tell you a research project that we have been conducting in the Tucson Sci-Fi group, which is that in the early days of science fiction in the 1920s and 30s, the idea of micro robots that could self-replicate was already being discussed by science fiction writers. There is an American writer called Raymond Gallun who was writing in the 1930s, but there are references to Russian stories that were before the 1930s or right at the beginning of the 1930s. Did you ever read when you were in Russia?
I read so much. Probably I did. I read zillions of science fiction stories, right? So, yeah.
Okay, we will maybe later we will get you involved in this project, and you can help us find some sources that we have not seen before.
Sure. Yeah. I mean, yeah. Maybe something is not translated. Sure. Yeah.
Yeah. Cool. Okay. I have to run, but thank you for a wonderful presentation, and we will be in touch.
Yeah.
Bye-bye,
Thank you, Bruce. Thank you, Bruce.
Yeah, now, anybody else that has a question? I don't know if Coster Malaya is able to speak. He can type his question, so.
I have a question.
Yeah.
Oleg, perhaps you answered this, but it's not one thing. My impression is that these structures, you have a lot of pieces, and you've assembled some, but there's some fundamental step you still need to get to where you're starting to truly make these kinds of structures that you envision. Can you elaborate on that a little bit, or did I get it wrong?
It depends, right? So so if you ask me, for example, I want to get structure which looks like that, can you make it? Answer is no, because we didn't really achieve the full level of control. Would be you have a blueprint and you tell me this is my blueprint, make this type of structure. We're not yet. That will be engineering. We still in a scientific reality. We're trying to figure out what principles we can use to make completely arbitrary type of structure. But there are some various structures which we can make deliberately, and we in the process of establishing really principles how to make anything, right? So we're not yet there, but at least I can see, I believe it's feasible, and I can see that it can be achieved. There is another component is, even if I'm saying we can make some structure, you can ask, okay, but how big those structures, how many defects those structures will have, so all this kind of a bit more practical questions. And so I would say they're not perfect, right? But they can, be already something which you can see by naked eye, or with a simple microscope. They will be, maybe 100 microns. So that's already, relatively big structure which contain, millions of those components, which is already not small. In another aspect, which is I didn't discuss at all, we developing, you can imagine that all the structures might contain many different components, and then at the end of the day, there is some human which is supposed to pipette different components, which becomes not very effective. So we are developing also robotic approaches. So you can envision that now we have a robot which can mix different things together, can measure something when it's doing, decide what's need to be done. Again, it's not something which is kind of already realized, but we already have some prototype of this type of robot which can do this. So I'm trying to stress it more from the practical point of view while I'm showing pictures where it stands kind of in reality. I hope I answer your question.
Yeah, you did. It still sounds like, I'm just trying to think of some practical uses for some of these techniques. One that comes to mind, in optical telecommunications, we do a lot of, we can model nanostructures for use in optical telecommunications, because the wavelength of light is on the order of half a micron, okay? You use nanostructures to make devices like, you can use them to make devices like splitters, couplers, all these things to put together telecommunications networks. But one of the limitations has been our ability to actually make these nanostructures. We can model them beautifully and we can design them, but frequently we can't actually fabricate them because we get down to where they need to be structures that are on sub-micron scales, maybe not nanometer, but still quite a ways down there. And our ability to fabricate them is quite limited. So I'm just trying to see a connection with what you're doing with how fabrication of those structures could make an enormous difference in what is the backbone of all telecommunications throughout the world right now.
James, you're absolutely right. And we even have several proposals kind of along those lines now, where we're essentially saying, yes, people can calculate this and design them, but they cannot realize. And so there are various areas related specifically to optical. That's something which is actually of our high interest, because it doesn't require electrical conductivity and other stuff which complex on their own. And so some of them, for example, we had various kind of scientific results. We show, okay, we can manipulate how light emitted by one quantum dot, or we can envision how, and specifically actually about what you have been discussing, we have some proposals which discuss specific, realizations. The whole point is that you absolutely right that not possibly, it's not possible, it's extremely difficult to fabricate. And so, yeah, that's something which is of high interest. And again, I don't want to go into the technical details here, but I fully agree with you. And yeah, that's something which we're working on.
I'll be interested to see where it goes. I'll be very interested.
And so
I'll
will
be
I.
happy to share with you some. Yeah.
I have a question. Thank you for a very fascinating presentation.
Yes, no.
Yeah. But and it's almost indirectly a follow-up for the previous question. What are the applications that scientists like you and others that we're dealing with? What is the purpose? What is the? I mean, I can see the the statue, and we want a statue, and then car assembly and carving and all that. Where are we going in this nanoparticle assembly, self-assembly? Where are we going? Is it, what kind of applications are there for it?
So the simple example which I can give you is just as example, right? So if I ask people, what's the application of 3D printing? I mean, there are zillions of applications of 3D printing. 3D printing, it's a different way to manufacture stuff, which was not possible. So I envision what we are working on along the lines of what I was discussing is not geared toward one application, but it's establishing the fabrication platform for some kind of echo, I don't know. It's only me or it's everybody. Yeah, so establishing a fabrication platform to control really materials on small scale. Now, specifically, what I didn't, I was kind of referring more to the optical, is just because this is one of the probably the most which we have been working on. And there are a variety, again, I don't want it to sound too technical, there are a variety of materials with interesting optical properties which not possible to create now because we cannot really do it kind of one by one particle in specific places. So some of those known as, you know, optical metamaterials, they have a variety of properties, you know, depending on their structures. They can bend light in a particular way. I'm not sure why there is some kind of echo. So let me, yeah, we'll disregard the second. So the other applications which we have been working on, which I didn't discuss, more related to the questions how we can use it for delivery into the cell, because that's something which is kind of obviously interesting for a variety of therapeutic applications, for example. And this is where essentially having, for example, DNA frame, you don't need to have a larger scale structure, but to have DNA frame which can carry some kind of cargo, and how this can be used for delivering, for example, RNA or DNA into the cell. That's something, one of the interesting aspects. Ability to make mechanical materials with a complex architecture. Again, we all know that, you know, the strength of the bridge to some degree, to large degree, depends not only on the material which you're using, but in specific architecture. There are a variety of effects associated when you're going down in a scale of the materials. They start to deviate from the conventional macroscopic behavior of those materials, but how you engineer this type of architecture. For example, we have some unpublished study which shows that you can really reach the limit or kind of best performance through this ability to engineer 3D materials. There are a variety of questions, again, in not something which we do immediately, but something which we say we having ability.
Is the head?
Having ability to engineer materials which has different kind of chemical performance. So it does require to organize them in a particular way. So again, what I wanted to answer, it's not one application. It's not a range.
Excuse me, could I interrupt a minute? James Doty, could you please mute your computer? And Phil, oh, Phil already did. Okay. James Doty, we need you to mute. Can you hear me, James? Okay.
I think it's Costner.
We invited the excellency, the President of Zambia, Mr. Harry to come and be part of this historic and momentous occasion, where for the very first time, revive the history associated with this place.
Pastor Malaya, you need to mute yourself.
Coster Malaya, please mute your microphone. Coster. I don't know if he can even hear me.
Gloria, you have to go to your own computer to mute.
I
her.
can't see the screen. Something happened on my computer, so I can't
I
do
see.
anything about it, unfortunately. I don't want to disconnect everybody by messing with it.
Hello, Gloria.
Coster, I'm going to send him an email. Let me go and send Coster an email.
Are you getting me, Gloria?
Let me connect you to Mr. Mlay.
I have a question.
Yeah.
How many people are actually working on this sort of
Hello, madam.
technology?
Oh, he's-
At what levels? How far has it gone into engineering?
You mean in my group or in general in the world?
In general, in the world, I want to have some idea of how popular, how up and coming this is.
In general, kind of probably, I would say maybe like 100 groups on this order.
Madam, talk to Mr. Mlay.
Hello, madam. Hey, I'm at the head this place. There are some two boys who are sick. The other one is critically ill. Maybe you can go with them also. I think they will just test, but let them test him for COVID as well. Mr. Stumbeko, I think Mr. Stumbeko should come.
At this point, I think I'm the only one who is not muted. So yeah, so
I would think that this whole technology would be very interesting to a lot of people because it's obviously cutting edge and it has many possibilities. So I'm surprised to hear that there are only really 100 people working on this sort of thing worldwide.
sometimes it's difficult to know exactly, right? So, but sometimes it's also how exactly you cut the line. But I can tell you that if you ask how many people have been working on this, let's say 20 years ago, then you would say maybe 10 or something like this, whatever. So it's the number grew up significantly. So I don't know if it's 100 or hundreds, but it's kind of in this, yeah.
There's no journal dedicated to this yet.
No, there's no journal. Yeah.
Maybe
Still science fiction.
Maybe the question was how many people are working on self-replicating or nanoparticle systems?
That's a different, okay. If I'm saying this broader, then many, I don't know the number. On nanoparticles, I'm sure thousands and thousands of people working on different ways to synthesize particles. Now, there are different ways to organize particles using polymers, using that, using surfactants. There's a variety of different things. So why I started to work in this area maybe like about 15 years ago, because I saw despite variety of ways, you can create different type of structures, but you don't really have a control. So what was for me the most exciting to think about this way is that we can really program. So we have a very deliberate way how we can create structures. You can create kind of different type of organization using different methods, but it's just, it doesn't give you this designability. And this is what we are really striving to achieve here. In terms of self-replicating, I don't think really in terms of material we are there to create. Maybe there are a couple of people who has been trying somehow to do it. So self-assembled, yes, but not self-replicating. So that's not something which is, again, I wouldn't say that completely not, but it's just only maybe a few people who have been started thinking about this, and it's typically in a relatively simple systems.
And if I may ask a follow-up question, this self-assembly or self-replicating, are you envisioning it happening in a lab in order to produce other, systems, nanoparticle systems? in a confined environment when you provide the ingredients, and or also inside a biological system like a human body?
It's a good question. I personally not interested to do anything inside of human body. So it has been, some people were interested not in the human body, but for example, to hijack the certain processes which are occurring, for example, in simple cell organisms like in bacteria and so on, that they will produce, for example, and self-organize some machinery already and take them from them. So essentially to outsource the work to them. And so, but again, I don't think related in terms of human body, but in terms of cells, simple cell organisms, that's kind of has been. Our interest is not to go into this direction, but because we have some kind of more interest in creating in a long term complex artificial systems with all this ability to, you know, what I was discussing, and so that's kind of really what we are after.
And if they escape these systems into the air and the biological system inhales it,
yeah,
or goes through the skin,
yeah,
what are the implications there?
It's a good question, and I don't think anybody can tell this to give you the answer, but I can tell you approximately. Nanoparticles, again, without any DNA, without anything, nanoparticle on its own, there is a number, maybe for the last 10 or something like this, maybe a little bit more years, it was a lot of research going on about nanotoxicological effects. So the questions how nanoparticles can penetrate into cell and so on. There is much understanding and in this area. And in reality, the summary would be the property of nanoscale materials different, not only in the way how they look like, what I was showing, but in the way how they interact. Gold, will be different if it's 10 nanometers versus 1 micron and so on. So all those effects are, something is known, something is understood. There are a variety of different things which not kind of yet understood. In general, the guidance, there are certain guidance in terms of materials. The overall general guidance that materials which can be dispersed in air are considered kind of always toxic and dangerous because we simply don't know enough about them, and in some cases kind of know they can be dangerous. So for example, in our own research, when we're working with those materials, they always stay in solution, and so there's no very little probability for them kind of really to escape anywhere. The interaction with the skin, again, if it's depends on the nature. If it's, let's say, cadmium particles, yes, it's not a good idea. If it's gold particle, it's much less dangerous. Still, it's not a good idea to take a large amount. As soon as we're going and discussing more complex system, it's not just nanoparticle, but nanoparticle with DNA and all other stuff. I don't think there is a full understanding what body can do with this and what will be effect of this. It's known that very small particles can be clear, some larger particle can stuck in different places. So yeah, I can talk for longer, but I don't think that I'm going to give you more precise answer. Just from the point, it's not necessarily everything.
Maybe the question is there any attempt to provide legislation that will restrict what you're doing as opposed to your own considerations of dangers and ethics and so on?
Yeah, but we have very strict safety rule in the way how we work with those types of materials, what we can do, how we dispose them. So we're following. So there are plenty of regulation already, and so but all those regulations, they essentially not necessarily towards the full understanding how it's interact with the body, but basically saying we don't know enough, so we have to treat those materials as a dangerous materials. So you just take kind of a safer approach to this.
I have, sorry if I have another question.
Sure.
In the gold example, you have these nano, at the nanoscale, they have different properties, different colors, different thing. If you build, I don't know, maybe I'm completely off here, but if you build a system using, 3D system, you pile these nanoparticle gold into a visible chunk that I can see. Would it be gold, like, golden color, or
No.
it won't?
No, it likely will be kind of like bluish black color, kind of like that. So yeah.
And it won't be that expensive, or probably expensive
No,
because
it will be expensive. It will be more expensive than gold, not because of the gold only, but because of all this kind of processes involved, right? So
yes, yeah. But none of its properties, this not rusting, none of that. It would be a different animal.
right, it will be different animal, right? It's not, again, it has connection to gold, and one can calculate, and people have been, again, I don't want to sound too technical and so on, but people have been trying to understand and calculate, right, specifically in optical applications, but the properties are different from what you would expect from conventional, gold, the way how you imagine gold to be.
Interesting. And can you reverse it?
I'm sorry?
Can you reverse the process?
What do you mean reverse? If you can, by having nanoparticles, can you go back and just get create piece of gold out of this? In principle, you can, but it's very labor consuming. So this gold will cost much more than
yes, of course. It's just, I was just thinking about it.
Yeah, but it is possible.
Interesting. Wow. I mean, yeah. Well.
Okay.
I'd like to say thank you very much, Oleg. It was.
Well, I want to thank you, and I'm sorry we have to keep switching people in the chair here, but we had a problem on my computer, so this is my husband's computer. So I think if you all just leave, I won't be ending this. I don't know if anybody else, does anyone else have a question, or are we done? Looks like maybe we are about at the done point.
Yeah,
so what I'm going to do is just say, because I can't end the meeting for everybody, you can just quit the meeting individually, and then I will quit the meeting, and that will preserve the recording. And so we will have a recording, which as soon as Dan Brock gets them together, we have 3 now, a collection of 3 recordings. So please excuse this little glitch that happened on my computer. It's kind of a recurring problem. We have to figure it out. But I thank you all for coming, and we had an excellent presentation.
Absolutely fascinating. Thank you.
I am glad that we were able to do this and that you could come. So please don't take my ineptitude as any kind of comment on how happy I am that you could be here.
Thank you.
And all of you, James and Tim, all of you, I want to thank you for coming and making this, it's worthwhile, because it is so far from what's going on, for instance, I think in Tucson, that, we just don't know the cutting edge things. So this is very, very good.
I may contact you, Oleg.
Yeah, absolutely. Yeah, sure. It's easy to find my email. You can, or
I saw it. I wrote it in one of your slides. Yeah.
Yeah, please feel free. Sure, absolutely.
Thank you.
Thank you for your interest, guys.
Yeah, thank you. And anytime you're all ready, you can leave, and then I will just exit.
Thank you, Gloria.
Oh, you're very welcome. Yeah, I'm happy to be here. And those who are apparently still with us, it says we still have 5 people. Anytime you want to, you can just log off, take yourselves and go.
Thank you.
And
bye-bye.
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 Thank you, Gloria. Thank you. Bye-bye.
Bye-bye. Coster, are you able to hear me?
Yes.
Oh, that's you.
Yes.
Yeah. Okay. Yeah. Thank you.
Yeah, that's really
good. I'm reverberating.
This has been a very interesting presentation.
Yeah, I think he did a marvelous job. He came very prepared, and I just wish I hadn't had this problem with my own screen. But the last time it happened, it did save the recording, so we're okay. Thank you for coming, Coster, all the
Okay,
way
thank you.
from your home, and have a good rest of today. Bye-bye.
Okay, thank you. Thank you. Bye.
Bye. Now I'm gonna exit myself. 'cause I-
Just reboot your whole machine.
Down.